So let's talk about some tools that you'll use. One of them is, of course, your operating system. And for this class, I've settled on Ubuntu 22.04 or Ubuntu 23.04, which just came out. It came out after I made these slides, so they say 22.04, but I'm going to be using 23.04, and I always recommend people use the most modern good stuff, so I'd recommend you do the same. We're going to be on the x86-64 platform, sometimes called the AMD 64 architecture, and that is just a 64-bit processor architecture based on the older x86 32-bit architecture. It's an instruction set architecture, so if we say ISA, we mean instruction set architecture. It's just a way of representing the instructions, which instructions are available, how they're encoded, etc. In reality, nearly every processor version is different. They have different instructions or slightly different cycle times, or there's different stuff about them. We don't want to get into all that, so we're going to try to stay in the sort of the comfort zone of the x86-64, the common instruction set. Now you can run Ubuntu with the AMD 64 on VirtualBox, and you can actually run it on an M1 Mac, and I've done that. And that does work. An M2 Mac, I haven't tried that explicitly, but it seems like it should work. There's a tool called UTM that some people have used. I hear good things about it. I have not tried it. So what I recommend you do is get VirtualBox, which you can get from the link, and install it. It's a free tool. It basically is a virtual machine platform similar to VMware. And get Ubuntu, which you can get from the link, and install Ubuntu 23.04 in a virtual machine under VirtualBox, and then you'll be good to go. I strongly recommend you don't use the Windows subsystem for Linux, WSL. Someone tried that last time. It didn't go well, so I'd recommend you use a real Ubuntu installation. Why are we doing this? Why use Linux? Why not use Windows? Well, first, Linux is free. Not everybody has free access to Windows. And second, anyone can run it, and they can run it on nearly any hardware that you've got. And that's pretty great, right? If I've got a Mac, getting a virtual machine with Windows on it is going to be tough because I've got to maybe get a Windows license. It's going to be hard. But with this, anybody can do it. And why are we on the x86-64 platform? Well, it's still the dominant desktop platform. And so a lot of the stuff that you'd be using reverse engineering to deal with would probably be on that platform. But there's some good pedagogical reasons to use it. It's got a lot of idiosyncrasies, and that makes it an interesting assembly language to look at. ARM certainly has its own idiosyncrasies, but really x86-64 has the motherlode. It has basically everything that you'll see. And of course, everyone should be able to have access to it. You've almost certainly all got an ARM processor, probably in your pocket right now, or somewhere within a few feet of you, and maybe on your wrist. And that's great, but not everybody has a laptop that has the ARM processor in it easily and readily available. And even if you have a laptop that does, like an M1 Mac, which is based on the ARM, you can still get the x86-64 on that. Running ARM on an x86-64 is harder, so we're going to stick with that. 64 bits because the world's 64 bits, and it has been since the 20th century, right? In 1999, that was the year the 64-bit x86-64 was introduced. The first one was the AMD Opteron. There's a picture of, I think, mine down there. It was released in 2002. So it's not like this is a brand new thing, right? And you can even see on that little image, it says copyright 2001, right? We're in a 64-bit world, and so we should be using modern stuff. For your environment, you're going to need the binutils package. So at the prompt on Linux, you will do this: sudo apt. That's the Linux package, or that's the Debian package management tool, this is getting complicated. That's a wrapper around the Debian package management tool. So sudo lets you become root. Apt works with packages. Install installs a package, and the packages you want are build essential and GDB, which is a GNU debugger. I think you get GDB with build essential, but it's nice to do this just to be sure. An object file is something I'm going to talk about a lot. And what that is basically a file that contains machine code or raw data. Okay, it could be either one, could be both. Typically, it's created by an assembler or a compiler, but it doesn't have to be. You can put hex bytes in a file, or you can edit it in the hex editor, or you can whatever. You have a tool that creates it, right? Basically, compilers and assemblers are just themselves tools that spew out bytes into a file. You could do the same thing. The objdump executable, which you'll get when you install binutils, lets you look at the contents of object files, and it supports a lot of common object file formats. So you could look at files on Windows, on your Mac, on Linux, on Solaris, what have you. We're going to use this command a lot, so I recommend you take some time and get familiar with it. If you just do a man on objdump, or objdump-h, capital H, and it will tell you about it. If you do objdump with the lowercase h, it'll complain because that's the section headers flag. So capital H is how you get help for objdump, or man objdump. And some useful, helpful stuff is over on the side. Capital H is help. D will disassemble parts of a file. H will list the section headers that are present in the file. R shows relocations, T shows symbols, and W uses the wide format. We'll talk more about this as we go on, and so you'll get to see how some of that works. So if you just use objdump by itself and tell it something like H for headers, it will display a table of the headers. Now, there's lots of information in the headers, and so it can't easily show that in one line, so it wraps it. And so you'll see here, we've got size, VMA, LMA, file offset, align, and then the flags are shown on the next line. But they're really part of that same line. Same thing as doing high data, so that each entry takes up 2 lines, which is an okay way to display it. But if I use the -W switch, now the flags get their own column over here. I just have to make my window a little wider for it to work. So let's talk about computer architecture. Computer architecture is going to be very important to this class, and we're probably going to have to go into computer architecture maybe a little more deeply than you've done in the past, just to be sure you have a really good grasp on what's happening. However complicated you think computers are, they are more complicated than you think. And so part of the reason we go into this is just to hammer that point home. Whenever there is hidden complexity in something, there is often the capacity for someone to conduct some mischief, right? There's the opportunity for a vulnerability. And so we have to watch for that. Let's talk about memory, instructions, and the fetch-decode-execute cycle. So if you've had a basic computer architecture class, this is going to be familiar to you. You've got a processor that sits there in the middle and talks to everybody else. You've got memory out there that stores information. You've got input-output. These are all connected up by 2 buses. There's an address bus with some control lines, and there's a data bus, and the processor talks to everything else on these buses. There are many other buses in your computer as well, right? You may have an ISA bus. You may have SATA buses. These all have their own protocols and ways of communication and arbitration, but we're going to ignore all of that. In fact, we're going to ignore I/O for the most part and just focus on what's in the very basic system. If you want to know what's really going on, you can dig a little deeper with some of the links on this slide. This slide is an aside, which means I don't expect you to internalize this and learn this for the test. This is just something I think is additional interesting information if you care. Modern processors are more complex than you think they are, and it doesn't matter how complex you think they are, you're underestimating it. They are so complex that they basically are themselves networks of computers. So a modern processor, a modern desktop processor, is itself a network of other computers, of other processors. And these can be RISC processors, which can have their own memory, which can have their own internal instruction sets that may be different from the processor's instruction set. Well, will be different from the processor's instruction set. They have microcode that they can read that's stored on there. In fact, Intel can patch your processor with new code. A network? Yeah, they have a network on there. So older Intel chips used a ring bus. Modern ones use a mesh interconnect, and AMD uses something called Infinity Fabric. And if you want to read about all that, I gave you some links that I think are pretty good discussions. In some cases, high-level discussions, maybe a little more detailed in the WikiChip ones. But you can have a look at that and get a sense of some of the complexity on these. Modern processors actually run their own operating system. The modern Intel chips run a version of Minix. It's just a concession to how complicated these little beasts are. If you want to understand how a processor works, I recommend Ben Eater's videos. He builds really fascinating stuff on breadboard with wire and a few chips. He's built a graphics card. He built an 8-bit computer. It's just really, really fun stuff. You can sort of think of this as ASMR for nerds, but I recommend them. Here's the model that we're going to use for most of the rest of the class. We have a CPU that talks to memory. That's it. That's what we're going to primarily look at. And the way the CPU will do that is it will send addresses to memory. It will set read-or-write lines, and then memory and the CPU will communicate over a data bus. Memory itself will look like an associative array. There'll be addresses and there'll be data and instructions stored at that address. So what we have is data commingled with instructions. They're all sort of stored together. And we call that the von Neumann architecture, okay, where you have data and instructions together in memory. It's not the only one. We can have a Harvard architecture. In a Harvard architecture, we try to separate memory that contains instructions from memory that contains data. So data has its own memory, instructions have their own memory. We tend to think of the von Neumann architecture as being what the x86 is. That's partially true. And we tend to think of the Harvard architecture as being what ARM is, and that's partially true. Neither one of those is explicitly true. Modern processor architectures tend to be a hybrid, and we tend to lean more and more closely to the Harvard architecture. And the way that shows up on the x86 family of chips is with memory protection. I can mark memory as executable, instruction memory, or not executable, data memory. And I can do that with the no execute bit, sometimes called the NX bit. So just keep those two in mind. So your processor, regardless of what architecture you have, usually operates in a fetch, decode, execute cycle, and that begins by fetching some stuff from memory. So we have some information. Somehow we've gotten an address. By startup of the machine, maybe there's a defined location where we always start. Maybe there is a defined address whose memory contents contain a location where we start. Maybe there's some other way that this happens, but somehow at some point, the processor gets a location where it needs to begin to fetch instructions from memory and execute those instructions. And so it keeps track of this with an instruction pointer that holds a memory address. Fetch goes and gets the next instruction at that memory address and loads the bytes that make up that instruction into the processor. Once they're there, the processor has to decode them. It takes those bytes and it converts them into a schedule of micro operations. Modern processors, even RISC processors where you have a fairly simple instructions, a single instruction is broken down into many sub instructions. Things have to happen. Something has to be fetched from memory. Stuff has to be put in registers. Different circuits have to be connected, right? I want to put these things in registers and then add them using an adder. So I have to get access to one of the adders on the processor, get the result, and put that somewhere, maybe write something back out to memory. A whole schedule of operations is built for each one of these instructions that's fetched. Once I built that schedule through decode, I execute it. I do that set of tasks. And when I'm done with that set of tasks, as part of that, I will update the instruction pointer, and then I will just fetch the next instruction. And I go around and around and around and around this cycle as long as the processor is operating, and just keep fetching, decoding, and executing. Because if I ever stop doing that, well, then the processor just stops, and now I've got to reboot the machine or power cycle it or something else. Along the way, I mentioned the instruction pointer. This is a very important little thing. It's a register, which is basically a named piece of storage in the processor. And this one's special. The instruction pointer is sometimes called the program counter, is a special register that holds the address of the next instruction to execute. That's almost always the way it's implemented. In early machines, sometimes things were a little different. In modern machines, this is the way we've settled on to do it. The instruction pointer points to the first byte of the next instruction to execute. That is to say, it contains the address of the first byte of the next instruction to execute. Or, as you'll see, what is probably the next instruction to execute. The schedule of operations may change that. Okay? The address that is in the instruction pointer at the start of the fetch, decode, execute cycle is the address used for the fetch. That makes sense. Instructions can modify the instruction pointer during their execution. And I think that makes sense too. An instruction might say, I want to jump to a different address in memory and continue executing at that address. That jump instruction basically loads a new value into the instruction pointer, so the next fetch occurs at that address. And it is very common that the instruction pointer is updated as soon as the instruction is decoded. So the processor decodes the instruction, and then it updates the instruction pointer. That happens on the x86 because the processor doesn't actually know how many bytes long the instruction is until it decodes it. We'll see that in more detail a little later. But once it does, it can then change the instruction pointer to point to the address of the following instruction. So for example, if I go to location 1000 and load an instruction and it's 3 bytes long, then I can update the instruction pointer to point to 1003, which is the likely address of the next instruction. Again, a jump can change that, but that's the likely address. And that's in fact what most processors do. All modern processors, I'll say it that way, work that way. The x86-64 microarchitecture names this register RIP. No other register is the instruction pointer. I want to emphasize that because there are older versions that have 16 bits or 32 bits, and we inherit some stuff from them. And sometimes people can wind up using older versions or partial versions of the register. The RIP register is the only instruction pointer. That's the one you need. If you want to see someone on YouTube explain the fetch execute fetch-decode-execute cycle, excuse me, you can watch this excellent video where he'll explain it to you if you don't like my explanation. So let's think about interpreting an instruction. Fetching seems simple. We go to memory and get it. How do we interpret it? Well, first, let's start out and let's actually be sure we understand what happens when we fetch it. So the CPU has an address and it wants an instruction at that address. And so it puts that address on the address bus and it tells memory, hey, I want to read from the location. Memory's job is then to go to its file and locate the line that contains those bytes and take those bytes and put them on the data line for the processor to read. This is super simplified. It's not exactly how it works in the modern x86 processors, specifically because the CPU doesn't necessarily talk directly to memory. Remember, the CPU has a cache system. It talks to its cache manager. The cache manager talks to various buses, and they talk to DRAM. And we load memory by entire pages. So we'll talk about that later on. For right now, this is a good model. The CPU requests the memory, and the memory system hands it back some bytes. So we got back 16 bytes. And, it didn't make no sense to get bytes one at a time. Getting stuff from memory is very costly. We'll talk about why that may be later on. Very costly. You don't want to go all the way out to memory if you can help it. So we'll get a whole bunch of bytes at once. And then, in this case, we grab 16. We want to try to then interpret that. So are these 16 bytes an instruction? Is just the first byte an instruction? What makes up an instruction here? So as we look at it, we're seeing these bytes represented in hexadecimal. Hopefully you remember how hexadecimal works. So we have 4 Charlie as that first byte. That's 4 times 16, because that's in the 16s place, plus C. What is C? Well, A is 10, B is 11, and C is 12, right? We have to have digits up through 15. We only have regular digits through 9, so we borrow some letters to make that work. So that's 12. So that's 4 times 16, which is 64, plus 12, which is 76. So we know what that first value is. 03 is just 3, and so on. The nice thing about hexadecimal is every digit has 16 possible values. That means we need exactly 4 bytes to encode it in the usual way, which means 2 hex digits is exactly 1 byte. That's really perfect. So every 2 of those represents 1 byte, and so of course we have 16 of these pairs making up 16 bytes. In this case, it turns out the first 8 bytes of this thing we got back are the next instruction. They make up 1 instruction. So think about what we were doing here. We fetched all of this from memory. We start to decode it. We figure out these first 8 make up the instruction. And so once we've decoded it, where is RIP going to point? It's going to point right here. It's going to point to the address, first address following it. All right. Now, this is, of course, not how it works. I already hinted this a little bit. Memory is fetched by the cache controller. It's done in pages, etc. And the important thing to remember is it can take a long time for memory to get from DRAM to the processor. Just think about the fact that I have a bus that I'm talking from the processor to memory on, and I may have several different cores on my processor, or even multiple processors, and so there'll be contention, right? Everybody may want to talk to memory at the same time, and if so, I've got to figure out how to service all these requests, and that can become complicated. In addition, stuff has to be written back to memory, so that's got to happen. So all of that is problems. So what we do is we build cache. And so ideally, the processor just goes out to cache to get what it needs and doesn't have to go all the way out to DRAM. In order to speed things up even more, we do something called speculative execution. Instead of running the fetch, decode, execute cycle once, we run it a bunch of times in parallel. So we try to load, interpret, and execute multiple instructions at the same time. Now, we still want to give the illusion to the programmer that instructions happen one after another in the nice, orderly, lockstep fashion. So how do we do that? Well, suppose someone gives you a pile of work, and you realize, hey, this work can be distributed. I don't need to do all of it, right? Some of this work doesn't matter what order it's done. So you get some of your friends and you give them parts of the work, and they do, each one does a part of the work, and the work gets done in parallel, and that's great, right? The world's parallel, let's be parallel. That's wonderful. But suppose that while you're working on something, let's say that you've given everybody a whole bunch of different personnel documents, and they're all working on writing up information about these people. As you go into that stack of documents, you come upon one which shows that like several people have left the company. Oh no. So that means that the work being done on those people's files is no longer valid. So you've got to tell everybody, hey, if you have the file on these people, just toss it out. Sorry, that works can be thrown away. The same thing happens with the processor. The processor does work on an instruction and the one after it and the one after it as much as it can. And it may find out that some of that work isn't needed and it gets thrown away. For example, it may be doing work on the current instruction and the one immediately following it, but it figures out the current instruction is going to change RIP. It's going to jump somewhere. That means that the following work is not needed anymore and can be thrown away. This happens with conditional branching. You'll hear about how branching breaks the pipeline. That's why that happens. All this work is speculative. Okay, processors may try to do branch prediction. They say, I think we're going to take the branch or not take the branch, but they can be wrong. Once you've broken that, you have to refill the pipelines. That takes time, but in the long run, on average, you're gaining a huge amount of time by doing this parallel speculative work. So here's an example of that. This is all still on the side, but I think it's important to keep track of this. I've gotten an instruction. You can see I've loaded several pipelines over here. Instructions on the x86-64 can, if you want to get super technical, they can be any length because you have these prefix bytes, and you can put as many prefix bytes as you want in front of an instruction. In reality, that's crazy talk. The processor can't load an arbitrarily big instruction into memory. You have to pick a length, and the length that the x86-64 has picked is 15 bytes. So you can have a 1-byte instruction, a 2-byte instruction, a 3-byte instruction, up to 15 bytes. If you construct a 16-byte instruction with prefix bytes, the processor will issue an exception because it just doesn't have space for that. So we're limited to 15 bytes. But still, we don't know how long it is. It could be 1, it could be 15. So the processor fetches memory in chunks and loads the chunks into these pipelines. So here we've loaded a pipeline with F3OF1E-FA. We've loaded a second pipeline, 1 off. A third one, 2 off, 3 off, 4 off, 5 off, etc. And we're going to try to run them all. Right? We're going to try to decode and execute all of those. Now what you're thinking. What happens if we find out that we don't need the others? Well, we just throw them away. So for this first one, we figure out this right here is the branch protection endpoint instruction. It's basically a no-op. At some point, we'll talk about branch protection, but for now, it's just an instruction. We figure out that's what it is. It's just those 4 bytes, which means the next instruction in sequence is actually here, starting with S48. Now, what that means is all of those are invalid. So any work we did on those can be thrown away. The good news is we can keep the work being done down here because that's going to be the next thing we're going to do. So let's look at it. Oh, it turns out it's also 4 bytes in length. It's a subtract instruction, which means we can throw this away and the next one and the next one, and then go on to the next one. So that's basically the idea. Your processor is constantly doing work and then throwing a large part of that work away. because it can always gain performance by trying to do more in parallel. If you'd like to know about Spectre, Spectre is a bug that exploits speculative execution. You can watch this video by Paul Coker. So the fact that I did some work on an instruction, but I didn't need it, doesn't mean that all of the side effects of that went away. Right? I've got all those people in the room with me. They're all working on personnel files. I tell them, hey, throw these files away. And they're like, okay, we'll throw it away. But they're still a little grumpy because they did all that work and they had to throw it away. And so there's a little bit of a residue left of the work that we did but didn't get credit for. The same thing's true with the processor. The processor might load stuff from memory into cache. If it did, that's still cached. And we may be able to look at the time it takes to access memory to figure out what was loaded into cache. And if we do things just right, we can use that to violate protection rules on the processor. And he will explain it all to you. Assembly language and machine code are abstractions. Don't think of them as the absolute literal bedrock ground truth, because they're not. The instructions specify some work to do, and the processor is free to choose any method to accomplish the effect described by those instructions. It can do work out of order, so it can actually reorder the instructions if it wants to. It can do some before it, some later ones before it does earlier ones, and it may well do that. Think about just simple speculative execution. While I'm doing some instruction that takes a lot of cycles, I'm also trying to do a few that are later. They may get done before the one that's taking so much time gets done. So they're being done out of order. I can do extra work. I can go ahead and do some work that's not needed. And in fact, that's often what it does with speculative execution. My dog's excited. And it can do work and throw it away. It can do work you didn't ask it to do. It can do work that it can not do work you did ask it to do, and it can do work in a different order than you asked it to do it. As long as the overall effect is the same, the processor is free to do anything. The key takeaway that I want you to remember is, whenever the work schedule gets changed, you have a potential for a vulnerability. I often call these side channel vulnerabilities. There's a main channel on which we talk, and there's a side channel, which is the other stuff that goes on as a result of us talking. Modern processors always change the work schedule. Always. All right. Let's go back to our instruction, our 8-byte instruction, and let's decode it. So what does this instruction do? Well, this instruction takes the content of an internal register called RCX. So again, registers are named storage inside the processor. Somewhere there's an 8-byte piece of storage in the register file on the processor called RCX. And we go and we look at the contents of that, it holds 8 bytes, and we multiply that number by 8. Once we've done that, we take the result of that and we add it to the register RSI. So we take the content of RCX and multiply it by 8, add that to the content of the register RSI, add 512 to that, and using that as an address, fetch some bytes from memory. So think about what happened here. I took this register's contents, multiplied by 8, added it to this register's contents, added an offset of 512, used that address to fetch some bytes from memory. Then I take those bytes, I add them to the contents of another register called R8, and I store the results back in the register R8. Finally, I update flags. So your processor has what's called the condition code register, or the flag register. And these hold information about the most recent operation. If the most recent operation resulted in a value of 0, the 0 flag will be set. If the most recent operation overflowed, then the carry flag will be set. And there's a parity and a sign, which indicates that the last thing was negative in a 2's complement world, and some others as well. And we'll talk about those later on when we talk about conditional branching. So we know some stuff about what happened. So that was a lot. In addition, we left this part out. Let's go back and get it. The instruction pointer gets updated before the schedule of operations is performed. So we've built the schedule down here at the bottom. So we've decoded the instruction. So now we know the instruction is 8 bytes long. We know what we got to do. We haven't done it yet. But we also have to update RIP. And so we need to set RIP to the next linear instruction. So I'm going to say next linear. I'm going to use that term a lot. And what I mean is the next instruction in line. So right here. So we update RIP to point there. So that has to be done. Now, once we've updated RIP, we can then execute the sequence of operations. This will be very important later. If these operations refer to the value of RIP, it is a common mistake to think that because I'm in this instruction, RIP must point to me, must point to the first byte of my instruction that I'm executing right now. But it doesn't. It points to the first byte of the next linear instruction. So here we go. Fetch, the instruction pointer points to the instruction to fetch. Decode, we update the instruction pointer to point to the next linear instruction. Execute may further modify the instruction pointer depending on the instruction, and we repeat. Okay? So what this means is, you should always assume the instruction pointer points to the next linear instruction. Because the only time you get to think about what's happening is during execution of the instruction you wrote. And it's always going to point to the next linear one. Let's talk about assembly language versus machine code. So what you saw before, that string of bytes, that's machine code, okay? So that is something that the processor natively understands-ish, right? It knows about bits. It knows about signals on lines. And machine code, as we saw, has a very rich interpretation, and it's also nothing in that line communicates anything to me about what we saw that it did, right? I don't understand what those bytes mean. On the other hand, assembly language was created for human beings to read. Believe it or not, that is true. Okay, machine's doing fine with its bytes. Assembly language is created so that we can see what those do. And if you look at the assembly language, you'll see parts of all of that other stuff represented in there. For example, you'll see that there are register names, like R8, RSI, and RCX explicitly in there. You'll see that we have a mnemonic, which is a fun word. It basically just means a memory device, a way of representing what this instruction is. Add is an obvious one. Sub for subtract. Mul for multiply. Some of them are not so obvious. In fact, some of them are absolutely inscrutable. And they're not all super short. Some of them can get fairly long. That's just the way that it is. We just have to accept that. So assembly is the process of taking assembly language and generating machine code that represents that assembly language. So an instruction in assembly language down here, add something to R8 here, that is turned into this stuff up here at the top. Disassembly is the process of taking that stuff up at the top and packaging it as assembly language. Make sense? Assembly from assembly language to machine code, disassembly from machine code to assembly language. An important point is they're not one-to-one. It's very tempting to think, oh, this assembly language statement exactly captures the machine code, and the machine code is exactly captured by this assembly language instruction. And that is not true. It is not true. We'll come across a lot of examples over the course of the semester, and I'll try to point this out to you when it happens. Assemblers have optimization flags. What could they be optimizing if it was just one-to-one? So again, we're translating one language into another, and it's not going to be exact. The assembler is going to have some leeway on what it does. So what does assembly language or machine code, or what can you do with that stuff? What does it do? An instruction can read the processor state. Registers are a perfect example of processor state. The instruction pointer, part of the processor state. The processor has some control registers, and it has certain operating modes. And you can read all of that stuff. You can read from memory. Really, you're reading from cache, but you can read from memory. Another way to think about that that's maybe more correct is I can communicate with the cache controller. And in fact, that's more correct because I can do things like tell the cache controller to flush a line. I can write to memory. I can again talk to the cache controller. And I can modify the processor state. I can change the operating mode of the processor, or I can write to registers. And here's just another example of what I just talked to you about, right? Processor state and memory. Those are the things that you get to manipulate with assembly instructions. Now, assembly has input-output instructions, so we can think of it as manipulating input-output. We can also just treat that as part of the processor state. Let's think about control flow for assembly and machine language. The most obvious kind of control flow is the same kind of control flow you see in high-level languages. An instruction executes followed by the next instruction you see, right? A nice linear flow of instructions. If you're looking at a piece of code, you flow from top to bottom. There you go. Straight line instructions transform the processor state, and then they continue to the next instruction in the program. And they typically are going to set the condition flags, like the 0 flag and the parity and sign we saw earlier. They're going to set those, but they'll just keep plowing ahead. Over on the right there, you see an instruction at address 1202 hex. It consists of 2 bytes, 01 and D0 hex, and the instruction is add the contents of EDX to the contents of EAX and store the result in EAX. We'll get more into how assembly language instructions are encoded later, but that's basically what it does. We have an instruction, it's 2 bytes long, that's how it's decoded, and it's at address 1202. What is the address of the next instruction? This is a starting address for it. It's 2 bytes, so the next instruction should be at 1204, and in fact, that's where it's going to be. And that will be a 3-byte instruction. Okay, and so we'll execute it. The next instruction after that would be 3 bytes later. Another kind of instruction is a branch. So here at address 11EF hex, we have a 2-byte instruction, EB24 hex, and the instruction is jump to 1215 hex. All right, JMP is an unconditional jump. You can think of this as saying, I want to load this value, 1215, directly into RIP. Fine, that means that the next fetch will happen there, they'll decode and so on. I'll just point the processor there. That's what the jump instruction does. So what is going to be the address after this instruction executes? Well, it's not going to be the next linear one, right? It's going to be something later on. The next linear instruction is 11EF plus 2 bytes, which is 11F1, right? The next thing after F is 10, which is 16. And so we carry the 1. E plus 1 is F. All right, 11F1. Well, that's the next address linearly. And that's what RIP is going to hold during the execution of this instruction until we actually finish execution, in which case RIP will hold 1215. Okay. Now, this is a relative unconditional jump. So what it does is it takes the value 24 in hexadecimal right here, and it adds it to RIP, which we've already agreed holds 11F1. Not 11EF, but 11F1. So 11F1 plus 24. We can do that math pretty easily. 1 plus 4 is 5. F plus 2 is, right, F goes 10, 11, so it's 1. Carry the 1, which is 2, 12, 15. So this actually lets us specify this address as an offset. I point this out. It'll become important later on. And so that's what we do. This instruction jumps to a new address, and we begin executing at that new address. Here's a third kind of instruction. This is a conditional branch. So here at address 11F9 hex, we have a 2-byte instruction, 74OE hex, which is a JE, or jump if equal, to 1209 hex. So this instruction is going to check some flags and then make a decision about whether or not to modify RIP. Here's how that works. At the start, the instruction pointer holds 11F9 plus 2, right? So 9AB, 11FB. The JE instruction is going to look at the 0 flag, and if the 0 flag is set, meaning the result of the last instruction was 0, then it's going to take the jump, which means if the 0 flag is set, it will load this value directly into RIP, so that now RIP is looking at this value. So we add an offset. The offset is OE. We add that to the current value of RIP, which is not 11F9, but is 11FA, 11FB, 11FB. And we add OE to it. So what is B? Well, B is 11. And I'm adding E. E is 14. So I add 11 and 14, and I get 25. Okay, well, I overflowed at 16. So 25 minus 16 is 9. So I put a 9 down here. I carry the 1 up here. F plus 1 is 10. Carry the 1, 2, and the 1 plus 0 is 1. So the new address for this is 1209, which is what we see here. So that's the new address. What if the 0 flag is not set? If the 0 flag is not set, we don't modify RIP, which is already pointing to 11FB, and so the next instruction is the next linear instruction. And so that looks like this. Right? So if the 0 flag is not set, we go here. If it is set, we come down here. And this is just a simple conditional. And you'll notice here we have dashed lines. It's a common practice to use dashed lines for conditional jumps and solid lines for unconditional jumps. Not everybody does this, but a lot of tools will do that. Assembly language does not have the usual control flow primitives you're used to, like while loops and folds and so on. You'll have to build it basically using gotos and a few special instructions. So let's ask an obvious question. How many instructions are there? What do I got to learn? And the answer is a funny answer, which is there's not an answer. We don't know. And there's funny reasons why we don't know. So there are a lot. We know that. There are two main dialects for x86 64-bit instructions, the AT&T dialect and the Intel dialect. And really, they differ in how they describe the instructions. And if we just count mnemonics, there are 1,279 AT&T mnemonics and 981 Intel mnemonics. So this helps reinforce my point earlier that these things are not one-to-one. we already can't agree on how many mnemonics there are for the same operations on the processor. If we count in other ways, we can get different numbers. The real question is, every valid byte sequence, how many instructions are there really? And that's a lot, right? Too many to count? Are there too many to count? So a really clever fellow, Christopher Dumas, did this really neat work on breaking the x86-64 ISA by fuzzing it. It's a wonderful paper that I strongly encourage you to at least take a look at, that you can go and get on the Sand Sifter project, which is over here on GitHub. And he found tons and tons of interesting things in here. He found all sorts of undocumented instructions. He found all kinds of bugs and issues. So, even assemblers and disassemblers don't have the full range of behavior of the chip. You can download the software. It's really neat stuff. And his approach to doing it is just astonishingly clever. If you'd like to have him explain it to you, which he'll do a better job than I will, there's a video in here where he explains it. Assembly instructions, there's lots of them. I don't expect you to learn them all. You'll learn a subset of them, and hopefully you'll get good at looking up other ones that you need. Some of them are very specialized for specific purposes. Some of them are very general, and you'll see them all the time. You just need to know the basics, and after that, you can look up the special cases and deal with the rest of it. New features get added all the time, so the instruction set's going to change, and that's just the way that life is. Really? New things get added? I mean, how do compiler writers keep up? Well, they do lots of work to keep up. This is a poster put together by the people who maintain Clang and LLVM. And this is a poster about how they're going to support the Intel AVX 512 instructions. So your processor, 64-bit processor, has 64-bit registers. Great. It also has 80-bit registers. Really, for floating point. It also has 128-bit registers and 256-bit registers and 512-bit registers. Because, again, supports parallelism, right? I can cram a bunch of values into a single register and do operations on that register, and that results in me doing parallel operations on an entire vector, and that can be really, really powerful. The instruction set changes each time a new processor, or even different processor family, a product line comes out into the market, but that tries to maintain backward compatibility with the core set of features. Maybe that core feature set does change a bit over time, but we'll do our best. So let's think about running code both with and without the C runtime. This is going to be an important point about assembly later on. Trust me. There is a C standard out there in the world. You can go and get it and take a look at it if you, don't have a life. And it will tell you neat stuff about the C language that you might not otherwise know. So by definition, the main function can take nothing, or it can take two arguments, argc and argv. And you already know about those. And that's in the standard. And it also has some return value information, right? On program termination, the return type of the main function is a type compatible with int. A return from the initial call to the main function is equivalent to calling exit with the value returned by the main function as its argument. Or reaching the closing curly bracket terminates the main function and returns a value of 0. That's in the standard. So if you write your code and it complains and says, hey, you didn't return a value, you need to return a value at the end of your main function. No, the standard says you don't. It says by implicitly returning 0, you have done that. So, you know what? Compiler writers should read the standard. So here is a little piece of code. Ignore that top first line for the moment. We'll cover what that is in a later class. This is not a very complicated piece of code. It's pretty simple. What happens when you run it, right? So here's our main function. We have argc, argv, and this thing, envp. What in the heck? How is there a third thing? Well, on Linux, on Windows, on most platforms, there is a standard third thing, which is a pointer to the environment string table. And you can use that if you're interested. You don't have to. You don't even have to acknowledge that it's there. You can write your functions without it. I'm going to write mine with it because I like to enforce that it's out there. What we do is we call putS, which is, just like printf without all the fancy extra features. It just writes a string straight out. And we putS hello world with a new line. We return 0 and we're done. We can compile that and we can run it and it'll print hello world. And if we do an echo $? After it, it will tell us 0, return 0. This is a way of seeing the return value. What does the operating system do? Well, after we've compiled it and we run the executable, the operating system has to figure out what the heck we're trying to do. So it looks at the file, and it turns out the file is an executable file, so it maps it into memory. It sets up any data structures the program needs. It may require loading libraries or building arrays or allocating memory. And then we invoke the main function to start our program, obtain the return value, then we deallocate resources and we terminate. You all know all of this, I'm sure. A chunk of what just happened in that little list is actually managed for us by a part of our program that we didn't explicitly write, the C runtime. Okay, so let's take a look and let's see what's happening in the operating system as this little C program executes. And we're going to see that using a tool called strace. So we run this with strace, and it's going to show us every system call that happens. And as you can see, quite a lot is happening. So up at the top, we did our strace of hello, and we see an exec VE, which is just starting our thing out, right? So exec VE, we see we have hello as our first argument, and then an array of other stuff. And then that thing at the end, of course, is a pointer to all of the environment variables, and there are 34 of them. The next thing that we do is all of that. That is memory mapping stuff. So break is the program break. Break null tells us where it is. We can do some stuff with the memory bits. We access preload. This has to do with loading libraries. Hopefully we don't preload libraries. It can be a vulnerability. We stat a file. We do an mmap. We open some stuff up. Look at this. This is libc so6. This is a shared library. It's the C standard library. We read that in that 177 ELF. That's indicated we're reading an ELF file. We do some more stuff with memory mapping. We do some memory protection stuff. And then finally, after all of that work is done, we again check break, and then we modify it. Basically, we give the program a little small pool of heap. And then the write instruction is called by our program. Our program actually runs at this moment. Everything prior to that is the C runtime setting stuff up for us. Our program runs, and then we do an exit group, which is how you exit a thread group on Linux, and we're done. So you can also run without the C runtime. Two ways to run most programs. It can be directly started by the operating system, starts up a process, the process communicates with the operating system, and when it's done, it hands control back to the operating system. Let's think about this for just a minute. Our process is going to have memory. It's going to have a heap. It's going to have a stack. It's going to have all the stuff that a process has. That exists in virtual memory. The operating system is going to build a virtual memory map just for our process when it starts up. So prior to our process starting up, our stack doesn't exist. There is no stack for our process. There's no heap. There's no none of that stuff even exists, right? There's no universe for our process. It's all created for us virtually by the operating system, right? Our process is living in a simulation. At the end of that, it returns control. Once it does, the operating system removes our process from the scheduler, which means we're done. Nothing else will ever happen, right, for our process. We're just done. And our stuff gets deallocated and thrown back into the pool. Okay? So that's one way to do it. In fact, that's the only way it happens. This is what the operating system always does. Now, what if we have a C runtime? If you have a C runtime, that's actually part of our process. It's a little wrapper around our main function and other code that handles a lot of stuff for us. It sets up some data structures for us. It puts things in different places. It puts some values on and into registers. It sets up some other data structures. And when we're done, we can turn control back to the C runtime. That outer yellow box here is really just a process like any other. This is what the operating system, for all it knows, this is just a box. It doesn't know anything about the C runtime or any of that. Our process depends on this C runtime setting stuff up for us. And we'll see how that works a little bit later on. Okay, let's think about what assembly looks like with and without the C runtime. So here we have some assembly code on the right. This code is intended to be run as an ordinary process without the C runtime around it. And one of the tip-offs of that is that we see something called _start here, and we don't see main anywhere in here. Again, if we were expecting this to run with C, we'd probably have a main function in here, and we don't. So we can assume that this is meant to be just run as a process. So what does this piece of code do? Well, it prints hello world. And you can put it into a file called hello-noc.asm, and you can assemble it using NASM, which we'll talk about, the net-wide assembler. Assemble it for 64-bit ELF. That'll give you a file called hello-noc.o, just like compiling it would give you a .o file. We then link it with the linker LD. We get an output called hello.noc or hello-noc, and that gives us about an 8K file called hello-noc, which when we run it, it says hello assembly world. Now the stuff on the right doesn't have to make any sense to you yet. We'll go through all of this stuff at a later time, but that's basically what happens. Now we have a hello world program written in assembly that doesn't use the C runtime. Here's a version that does the same thing, prints hello C world, but it does it using the C runtime around it, or it's expected to have the C runtime wrapping it. And you can see one immediate difference. We have a main function here. And after we compile it, we wind up with a 16K file. Why is that? It's because we've wrapped this with the C runtime and other data structures that become part of it, and we now run it and we get hello C world. And the build process is slightly different. We do the same thing with NASM, but instead of just directly linking it, we'll call GCC. GCC will actually call the linker for us, but it'll add a bunch of options to link other files in that make up the C runtime. Let's take a look at running our piece of code that was just pure assembly without the C runtime, and let's see what strace shows us. And what we see is we have the exec_ve line. There we are with our various arguments. We write out the string and we exit. All that other stuff that happened before was done by the C runtime. We don't have that, so none of that work gets done here. If we want that work to get done, we have to do it ourselves. right? It does what it says and nothing else. Most programs you will encounter will use the C runtime because why wouldn't you use the C runtime? It's there, you've got it, just use it. Embedded programs, the C runtime itself, some operating system code, and malware might not use the C runtime or might use it in a way that's not the standard or usual way. And so because of that, you really need to understand both and how things work with both. Why are we doing this to ourselves? Assembly language is hard and it's not intuitive. High-level languages are there to make programs easier to write. So why analyze a program in assembly language at all? Let's convert everything to a high-level language and analyze it there. Well, we might not have source code. Malware authors seldom give you source code. Sometimes you lose the source code to something. You might want to modify Baldur's Gate so that you can do something. You can get past some hard part of the game in a different way, and the game company is not going to give you the source code. So those are some reasons. Decompilers are approximate at best. Decompilers try to take machine code and turn it back into a high-level language. Ghidra has one. Hexrace has one. You can download Ghidra for free. You can grab a piece of code and you can point Ghidra to it and you can see what you get out. And what you'll get out will be an approximation in C of what's really going on. And another thing to think about is that compilers are approximate at best. Source code is strong advice. The compiler may make some decisions that it didn't tell you about, and those may change what you see. So the linkage between the high-level language and the low-level machine code, and in fact what happens on the machine, that's not as clear-cut as we often like to think that it is. Compilers, just like the processor, can add, remove, and change behavior from what's in the source, and we'll see that. Here's a little program, tiny little program written in C. Here we have a little function called delay, doesn't take any arguments, doesn't return anything. We have two unsigned characters, I and j. We set j equal to 0, and then we pre-decrement it. And while that value is not 0, we set I equal to 0, and then we pre-decrement it. And while that value is not equal to 0, we run. And the question is, how many times does this little inner loop run? Well, this starts at 0. We immediately decrement it, so now it's 255. And so it counts down from 255 back to 0 and stops. And it does that every time the outer loop runs. So this runs 256 times. The outer loop runs 256 times. The whole thing is going to run 65,536 times. Let's compile it, and then we will disassemble it using a tool we mentioned earlier called objdump. So compiling it's easy. We just do basically this, gcc-o, and then we give it the output we want and the file name. We'll cover this magic line at the top later on. When we do that, we take the code on the left, compile it, and then dump out the result. We get what's on the right. And I've annotated with these little arrows so you can see what's happening. Again, solid arrows are unconditional, dashed arrows are conditional. So don't worry too much about the instructions themselves. I'll just point out a few highlights. One, we come in here, we jump down to here, we do a subtract. So that's basically subtracting 1 from something. So we're decrementing something. We check to see if it's 0, and if it's not 0, we come up here, and then we subtract, compare it to 0, and if we're not 0, we go here. Oh, look at this. This must be the inner loop. And then, when the inner loop's done, we fall down here, and there's the outer loop. So both the loops are very clearly represented here. Let's optimize it. So if we do a -O, -O, we apply some level of optimization to the code. In other words, we tell the compiler, think harder about what you're giving us and try to do a better job. So the compiler devotes more resources to it, and we wind up with this piece of code right here. It basically applies some additional algorithms to try to make our code more compact or to make it run faster, or both. And so here we have some code that comes in here. The compiler has figured out, so up here, the compiler jumped down here, sub compare, and then it came up here, these loops. Now the compiler has figured out it doesn't need that structure. It can just plow right into our do while structure. And so here's our inner loop, and here's our outer loop. Okay. Let's see if we can optimize it even further. Let's give it -02. When we do that, the compiler says nothing. The compiler eliminates our code entirely. It just removes it. So at this point, we have no code left. And so the answer to how much does that code run is it doesn't run at all. The compiler has figured out that our code doesn't reference anything external. It doesn't take any arguments that it can modify, and it doesn't return anything back to the rest of the program. So therefore, it has no lasting effect. Now, that may not be true, and in fact, it certainly isn't true. This takes time. If it executes, if, for example, this code executes, it takes time. And it's not uncommon to have delay loops in embedded programs. And so that's what we may be trying to do here, and the compiler is removing it. This is a common thing compilers do. Certain parts of code, delay loops, certain kinds of control loops, a lot of security code looks like it does nothing. For example, I might have a big chunk of code that overwrites a key or a password in memory to erase it. But it has no effect outside of that because the memory gets deallocated. The compiler may throw all of that away, and I have to watch for that. So again, this is a strong difference between source code and what I actually get on the other side, and a reason to take a look at the disassembly. If you analyze source code, you're analyzing an approximation of the real behavior. Compilers do stuff that's crazy. They can insert code you didn't write, omit code you did write, and change your code for a lot of purposes. They can reorient your code, reorganize it, etc. If you want to know what it's going to do, you have to analyze what's actually running. The output of the disassembler might not be true, but it's maybe as close as you can reasonably get. High-level languages are abstractions. The code specifies some work, and the compiler can do whatever it wants to do. It can change the work schedule. As long as it's the same, it can do anything. And whenever the compiler changes the work schedule, you have the potential for a vulnerability, and they always change the work schedule, especially with high optimization levels. Be wary of high optimization levels. That's it. Thank you very much.